This video we're going to talk a little bit more about motion and kind of combine some old ideas with calculus ideas. So dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height given by that equation after t seconds. How high does the rock go? Well, we could certainly graph it. You can see I have given a graph here below. It's a little bit, it is 400 feet is what it reaches. Maybe a little bit hard to see that, but if you remember from old, Algebra 2, if you have a general quadratic, by that I mean ax squared plus bx plus c, you can find the vertex using the equation negative b divided by 2a. So in our case, rewriting this in the kind of correct form, we'd have negative 16t squared plus 160t. So negative b over 2a would be negative 160 divided by 2 multiplied by negative 16, which is 5. And when we plug 5 back into the equation, we do get 400. And what that 5 means, of course, is that the maximum occurs when the x is 5, so we plug it back in. So the answer is 400 feet. There is a calculus way to do that. If you think about what the derivative would have to be at the maximum, the derivative up here would be 0 because the slope is 0. Well, the derivative of s, let me just kind of write this over here, the derivative of s is 160 minus 32t. If you set that equal to 0 and solve, you will again get 5. So there is a calculus way to do that as well that actually is probably easier than the quadratic way. Velocity when it hits 256 feet. Well, we have a velocity equation. I've written it, already over to the right here in blue. But we need to figure out when it hits 256 feet. It is 2 seconds and 8 seconds, it says on the way up. We could certainly solve that algebraically by setting this equal to 256 using quadratic formula. Or we could, actually graph it. We've got a number of choices. But the important thing is it happens at time 2. So when we plug 2 in, we get a velocity. Right on the way up here, we'll put this in blue, or red, excuse me. We get a velocity of 96 feet per second. On the way down, well, we could plug in 8 to our velocity equation, or we could use what we know about physics. It's going to be negative 96 feet per second. Okay. And remember, the velocity includes a directional component, so the fact that this is positive tells me it's going up. The fact that this is negative tells me it's going down. Acceleration is the second derivative. The second derivative would just be negative 32, and hopefully from physics you know that that is the constant attributed to gravity. Finally, when does the rock hit the ground? Well, again, you can see from the graph that it starts at 0, goes up, comes down at 10. You could also look at doing this with a little algebra. If you go back and to the original equation, you'll notice that you could factor a 16 and a t out and have 10 minus t. So if you're looking to make this equal to 0, t could be 0 or t could be 10. So that's kind of a nice way to do it. Well, now it hits at 10. We plug 10 into our velocity equation. We get, let me just write, v equals negative 160 feet per second. So the speed will be 160 because it's always going to be positive feet per second. Okay, just a quick review and rundown of the equations. If I have a position equation, remember that velocity is simply the derivative. So s prime of t is equal to velocity, which is 15t squared minus 7. Acceleration is the second derivative. Which is 30t. Now the third derivative, in this case, of course, that would just be 30. This represents what's called the jerk. Okay. Now, velocity is how position changes with respect to time. Acceleration is how velocity changes with respect to time. So the third derivative, jerk, is how acceleration changes with respect to time. So the units go, let's say inches, inches per second, inches per second per second, and inches per second per second per second. So there are applications to jerk. We don't use it a whole lot, but it's just the third derivative. Next, an ant's position's been taken every minute. Estimate the velocity at time 3. Well, the basic idea here, if I can just draw a quick graph, because we don't actually know what the ant's graph looks like. We only know these kind of benchmark values, that at time 1 it's 9 inches away, at time 2 it's 33 inches, and so on. But if you wanted to know the velocity, of course velocity is the derivative, which means it's the slope. So what we really want is the slope at 3. Well, let's say okay, I want the slope here at 3. Easiest way to do that using the graph or the table is to pick a point on either side and find the slope between those points. It'll probably give you a pretty nice estimate. So I'm going to find the slope between the points on either side. Okay, so difference in y's over difference in x's. And that will give me the slope, an estimate of the slope at 3. Finally, one more, how did we know that graph? This is Mr. Fry's velocity. Okay, so let's just kind of track our way through this. Positive velocity, so he's moving forward, then backward, then standing still, then backward, then forward. Okay. When does Mr. Fry change directions? Well, at time 3 and at time 8. Okay, so I'm going to put time 3 and 8. And how do I know that? That's where velocity changes signs. When is Mr. Fry, and again, velocity changing signs. Remember, positive velocity means forward, negative velocity means backward. So when it changed signs, we had a change in direction. When is Mr. Fry traveling to the right? Well, from 0 to 3, and from 8 to 10. And how do I know that? Well, that's where the velocity was positive, was greater than 0. Now, when is Mr. Fry's acceleration positive? Well, acceleration represents the derivative of velocity, so now we're saying, when does velocity have a positive slope? So here, here, and here. So every time velocity has a positive slope, its derivative, acceleration, will be positive. So from 0 to 2, from 4 to 5, and from 8 to 9. Velocity has positive slope. You could also say velocity is increasing. Finally, when is Mr. Fry at rest? Well, he's at rest when velocity is 0. Okay, so he's at rest at time 6 to 7. And the reason is velocity is equal to 0.